frequency. So you can have multiple frequencies being radiated, multiple beams, multiple frequencies. So very difficult to jam this sort of radars. And as I told you, it's multifunctional. Uh, it can scan the volume for like a search radar, and once it picks up a particular target, then it can start tracking it. Okay, so that's why it is also called as a track while scan radar. It can do imaging, it can do ground imaging, you name anything it can do. So that's why it's very versatile. And the radar, what we are trying to develop is called Uttam, UTTAM. That probably will be fitted on the Mark 1A, later batches of Mark 1A. But presently they are going for a ELTA AES373 radar. ELTA is a Israeli radar. Okay. So that's on the antennas part of it. Anything the class wants to ask me about this antennas, something which is bugging you? Sandita, is it okay? Basic concepts of antenna?
Yes, sir.
Yeah. Please go through the book, okay? Friends is sufficient
Yes,
for
sir.
this. So in a communication chain, we have this antenna. We know how the EM wave is being received or transmitted. Now the next stage is, if you are receiving it, it's going to be of very low levels, power levels. So you require an amplifier. Okay? And this amplifier amplifies the incoming signal. So you have V in and V out. So depending on the gain of the amplifier, which is given as absolute numbers, it will increase the level. So, so it's a single input, single output device. Okay? So if you give 0.4 volts and its gain is 10, so automatically it becomes 4 volts. Of course, you will ask me how this energy gets increased. Uh, it is not just it's not like an antenna, it's an active device. So you give power supply to the device, you power it up, so the energy level increases. So typically such graphs are given, input voltage versus output voltage. And you would like to operate it in the linear region. After some time, you can't operate it, and you'll find the graph going down, becomes saturated. So we have to ensure that whatever specification is given by the manufacturer, we will have to follow it. 1 year really doesn't require much. Uh, you will not go into the blocks of an amplifier, how it works and all. Uh, as long as you know that it's a dabba with one input and output and correct power supplies, that should be enough. There are different ways of amplification. Uh, if the complete sinusoid is amplified, then it is called class A. Okay, so basically, there are only two amplifiers which are used in radio frequency region. One is class A, and the other one is called class C. Uh, it is again an amplifier in which you don't amplify the complete sinusoidal wave. Okay. Uh, Theory behind that is a bit complicated. You will find it difficult. That's why I deleted that slide. But generally, you will find class C amplifiers in RF work. Oh, it's not really difficult. Okay. Uh, okay. See, what really happens is you give pulses. Okay, I'll leave it. It's a bit difficult to understand. Okay. Just remember that class C amplifiers are used in RF for RF amplification. Class A and all will be used in lower frequencies. So this is how it looks like. Okay. Uh, all you do is go and ask them how much gain you want, and then plug in, give the input from the antenna. This comes from the antenna, and this goes out. That's all. And give the power supply. That's all to it. Okay. Nowadays, all these boxes are available. Just look at the frequency range, ask for the gain, and then you just buy it. That's all. Okay. Okay, fine. Now you have done this. You have the antenna. Now you can amplify it. Before I send it to the mixer, uh, generally in RF work, we'll have one pre-selector filter. Pre-selector filter. So idea is you know how to calculate image frequency. This pre-selector filter will ensure that image frequencies don't go in. So it's and then you have this mixer and one more IF filter, intermediate frequency filter, and then demodulator. So filters, as the name says, it passes some frequency and rejects others. Okay, that's why it is a frequency selective circuit. Now let's understand how we are getting this plot. Sandita, from the plot, what can you say? How do you say it's a low pass filter? You said the title is low pass. Looking at the plot, how do you say it's a low pass? Forget about the diagram, just the plot. The blue line is the characteristics of the filter. Y-axis is what comes out of the filter, and here they are giving input with variable frequency. So this is frequency starting from 0 to 6000 hertz. Anyone from the class? Why it is called as a low pass filter? Looking at the graph, how do you say it's a low pass filter? What is 3 dB, Sandita? Minus 3 dB? Can you hear me, Sandita? Sarup, can you hear me?
Yes, sir.
I think she has not, she has to unmute her mic. Sarup, can you tell me why it is a low pass filter?
I don't know, sir.
No, looking from the graph. Filter is it's a selective frequency selective circuit. Okay, so it allows certain amount of frequency and rejects other frequency. So from the graph, how do you say it's a low pass filter? It is same as what you people did in
Select
Bode plot.
low frequency signals to pass and
Yeah, low frequency signals it will allow
these are
to pass.
damped.
Yeah. So if you look at this characteristics, this is zero frequency. Okay. After that, here whatever is the V in comes out as V out. Okay. But so it goes on till around 600 hertz. X-axis is 600 hertz. Then you see that the output keeps on reducing. And by 6000 hertz, if you see there's hardly anything, it is almost 23 dB down. And 3 dB down is nothing but half, okay, 10 log to the base 10 half. Okay, this is 0.5, that's why you'll get minus. So it's reduced by half. Okay. So the function of the low pass filter is all these frequencies it will allow to pass and others it will reject. And when you talk about bandwidth, we just say 3 dB bandwidth. So we say this is the bandwidth of the filter. Whatever frequency is there, so in this case it is 1200 hertz, 0 to 1200 hertz, it will pass. Any other frequency above that, it will start rejecting it or it will attenuate it. Attenuation is opposite of gain. Getting it? No? So that's why it's called as a low pass filter. Now let's see how this circuit works. Again, I'm just going back to a basic class 12 physics only. Okay. I have two resistances connected in series, and in between I take the output. So from your physics class, anyone remembers what will be V out? It's a potential divider, okay? Basically, it's a potential divider. When you connect two resistance in series and you take the output from the middle, then what will be the output? Okay, fine. And if you don't remember, it's all right. So it's nothing but R2 by R1 plus R2. Just remember this. You need not even derive it. It's not very difficult to derive, but this output voltage, if this had this been a resistor, is nothing but V in times R, this ratio R2 by R1 plus R2. So I'll just give some numbers. Uh, let's say V in is 10 volts, R1 is R2 is 1, both are 1 ohms, okay? So it is 1 plus 1, so you'll get 1 by 2, this will become output V out is equal to 5 volts. Is it okay, Saru? I'm just giving some numbers.
Okay.
Are you getting it or you're finding it difficult?
Sir, I'm not able to focus, sir. I have headache.
Headache. I know, afternoon. Sanjay, how about you?
Can you repeat it again, sir?
Yeah, sure. No, don't worry. Feel free to ask me, okay, in case finding it difficult. Okay. For the time being, I forget about this filter. Okay.
Excuse me, sir. I am
Yeah.
back. Sorry, my system got hung. I was trying to unmute, but I couldn't unmute.
Okay, okay, no issues. Okay, Sanjay, we'll forget about this filter right now. We'll talk about a simple potential divider. Okay, with potential divider is nothing but two resistances connected in series. And at this point, I'm taking out the output. Now, this V out from your 12th class physics is nothing but, if I call this as R1, R2, it's nothing but R2 by R1 plus R2. Okay. Is it all right, Sanjay, up to this?
Yes, sir. Yes, sir.
Now let's give some numbers. Let's assume that R1 and R2, they are both equal to 10 ohms. This is a symbol for resistance. And let's say input is 10 volts. So what will V out will be how much? 10 into 10 by 20, right? So it's again 1 by 2 is 5 volts. Is it all right up to this, Sanjay?
Yes, sir.
Yeah. Others in the class,
Yes, sir.
it is just an attenuator, okay? I'm reducing the value which was from 10 volts. So if I change this R2, accordingly this one is going to change. The output is going to change because the denominator is changing, that's all. Okay. Now, how do I make it? Resistances are not frequency selective, okay? They don't know what frequency it is operating. They just dissipate energy, nothing else. So if you use a capacitor instead of R2, I'll use a capacitor, then you get this sort of response. Now we'll see why it is so. R1, then I have a capacitance, and then earth. Same input, I take the output. Is it okay, Sanjay? I'm just replacing R2 with the capacitance.
Yes, sir. It's all right.
Yeah. Now, if you look at the resistance of capacitance, it's called reactance, XC. The moment you talk about reactance, it is frequency selective. So XC is given by 1 by 2 pi FC. So instead of R2, I put XC here and then use the same formula. Now, Sanjay, can you tell me how it's working? Or
So
anyone from the class?
since it is frequency dependent now, so some of the frequencies are allowed to move in,
Ah,
others are
yeah, now
attenuated.
why? Yeah, good. So why does it not allow the high frequencies?
The voltage will be very negligible, sir. Will be
Why?
attenuated
Why?
because the frequency is inverse. I mean, the reactance is inversely proportional to the frequency.
Good, good. So as FC increases, XC is going to reduce, right? Because as you told, it is inversely proportional. So what happens is, now here you put this as XC. numerator is going to reduce like anything. So V out is going to reduce. That's why you find that at higher frequencies, the gain reduces. Does it make sense, Sanjay? No?
Yes, sir.
Okay. Now, how will you convert this into a low pass, high pass filter? So high pass filter is, the characteristic is like this. Okay. It will pass all high frequencies. Whereas attenuate lower frequencies. So ideally it should be like this, a perfect response, like a step input. But there are physical systems you can't get such ideal characteristics. And this is called also the pass band, okay? Another term quite frequently used. It's open to the class, okay? Just think for some time. I'll show the previous one so that you'll get enough clues.
Maybe interchange the two, sir. Interchange the capacitor and the resistance.
Good, good. Just interchange the capacitance and resistance, you'll get this sort of characteristics. So you can work out on your own how this whole thing changes. Okay. Good. Sanjay. Okay. Now, a small assignment for you people. Using high pass filter and one low pass filter, you will have to design what is called as band pass filter. So it will pass a band of frequencies. This is called band pass filter. And then there is something called band stop filter. So it will allow everything else except this region, it will stop. It will not allow frequencies in this particular region. So you have a band pass filter and a band stop filter. Is it okay? But you are permitted to use only one high pass filter and one low pass filter. And it's not, you can't use more than one filter. Okay, Sanjay, next class you can tell me how you can do it. You got the question, Sandita?
Yes, sir. So we can
Using a
combine the two.
high pass filter and a low pass filter in some combination, you'll have to design a band pass filter and a band stop filter.
So, so we let the uh, we first place a high pass filter and then let it pass through the low pass filter so that we
That's
get
what
that
you let me
band.
know. You'll
Okay,
just draw it and let me know next class.
okay, okay.
Okay, it's for the complete class. You can all discuss together and then one of you can come and tell me what it is. Okay. So you have a low pass filter, high pass filter, band stop filter, band pass filter. So one, two, three, four. What is the fifth one? So there are actually 5 options. So I'm asking you what is the 5th option now?
Is it all
Sanjay, can you? Sorry? Yeah, come again.
all pass filter?
Good. All pass filter. Then why, if it is going to pass everything, why you have a filter at all? Very good. You got the answer. Can you just think one step more?
Probably it only reduces the noise and
Reduce, sorry.
like uh, the noise, unwanted things, and amplifies the gain or something.
No, then it will be called as, actually, it will be called as amplifier, right? And the
Yeah.
moment you say that it's removing noise, it becomes a filter. And it is what Sandita is telling, it is all pass.
So Akshay only said that it's all pass.
Oh, she only told it, sir. Oh, you didn't.
Yes.
Okay, Akshaya. Good, your answer is correct, Akshaya, but
I'm not
it's
sure of the reason, but I've heard of this filter. So
okay. Yeah. Okay, the main function of this good attempt. Okay. The basic function of all pass filter is to introduce some phase lag, lead, and all those things. Okay. So it passes all frequencies but changes the phase. And that's what we talked about in this phased array radar. No, I told you you can introduce phase lags or phase leads or phase change rather uh, to steer the beam. So these filters are basically used for introducing some phase change. And but they're clubbed under filters. It's called all pass filter. Okay, that's just for your information. Uh, And there are different ways of producing, manufacturing these filters. So what we saw was a simple R and then C. Okay, just one combination. You can have multiple such elements. Okay, R, C, R2, C2, so on and so forth. Uh, So depending on the number of elements you can have, the better will be the characteristics. See, ideally, if I say it's low pass, I would like to have characteristics like this, V out frequency. Okay. But when you actually manufacture a filter, it's going to be something like this, the green path. If you remember from your controls theory, each one of these combination is actually a pole. So more number of poles, better should be the response from your Bode plot. Okay, if you have multiple poles, so you keep adding the response. then you will have sharper responses. But unfortunately, what happens is the sharper the response, more will be the ripple. So these are called ripples. Okay, both in the pass band as well as in the stop band. So sharper the response, more is the ripple. It is analogous to telling that in an antenna, narrower the beam width, more is the side lobes. I told you, no, I just when we talked about antennas, I told you about side lobes. So it's again a compromise. Whether you want more ripples and a sharper transition, or you want a gradual transition without ripples. So accordingly, different researchers came with different filters: Chebyshev, elliptical, Butterworth, Bessel, and all this stuff. Okay, so but all you have to do is in the market just go and ask for a filter nowadays. They'll give you one box. So really don't start assembling R, C and all those stuff. So those days are all gone. So you just take the boxes. So this is how it looks like. Give the input and take the output. So this guy says it's a high pass filter. You go into the data sheet, he'll tell you up to what frequency it will pass, what frequencies it will attenuate, and then what frequency it's going to pass. So it's as simple as that nowadays. You really don't worry about how to realize these filters. That's all on filters. Anything you want to ask me? So in your textbook, it is page number 56 onwards, okay? 56 to 75. What I am having is a third edition. I don't know what is the page number in fourth edition. So this gives a good introduction to filters. Is it okay, Akshay?
Yes.
So please go through the book. Okay. And then next class we'll start with amplitude modulation, basic theory about amplitude modulation. Okay. Okay, thanks, Anita and Akshay. We'll meet in the next class.
Thank you.
Thank you, sir.